So code generation is kind of like the dark side, I guess, in a sense. And so I thought I'd call this not a story that the Jedi would tell you. I don't know if you guys have seen episode 1, 2. Anyway. So my goals here in this half an hour is to try and describe what code generation is, why it's used or where it's used, and just give you a bit of an overview onto 3 of probably the most common or becoming the most common technologies for actually generating code on the .NET platform. And that's expression trees, IL, which I'll go over, and Roslyn. So by the end of the talk, obviously you're just going to have somewhere to start. You're not going to, you should know where to Google, what to Google, and I've got some projects that you can look up on GitHub. But of course, it needs a lot of practice before you can, actually become a master at this. And I thought I should start by defining what code generation is. And I went to Wikipedia and I was like, CodeGen, this will be good. But it's got a definition for code generation, which is technically correct, but not the one I want to talk about. So what they're talking about on Wikipedia is code generation as a step of pretty much any compiler, where a compiler will read your code, it'll generate some intermediate representation of the code, and then code generation is the final step where it goes and generates, maybe it's x86 code, or in .NET's case, it might be IL, which we'll talk about. But that's not what we want. What I'm talking about is kind of more general. In a sense, code generator is a tool which takes some input. Maybe that's some source files. Maybe it's a binary like a DLL, or maybe it's like a proto file, if anyone's familiar with protocol buffers, which is a serialization library. And then it generates some output which is typically executed later. So it's source code, or directly generates an executable. And because we use a lot of code generation in Orleans, sometimes it might look like you start with a 30-line file, run it through our stuff, and you get 30,000 lines later. But hey, it saves you from writing those 30,000 lines, right? Now, code generation probably seems obscure, but I want to drill into everyone that this is used pretty much everywhere. So if you've got any non-trivial C# or whatever project, you're most likely relying fairly heavily on code generation. Every serializer that I know of uses it. JSON.NET, everyone uses. I have a typo, the binary format that comes with .NET. If you have an RPC, for making remote procedure calls like Google's gRPC or Orleans, which is what I work on. If you're testing, your mocks use it, Razor uses it, XAML uses it. Even DI libraries like the Microsoft Dependency Injection Library needs CodeGen so that it's not terribly slow. So it's crucial, but it's not magic. And the idea is that hopefully after today you'll sort of be able to get started and see how to decompose these sorts of things. And I want to focus just on .NET, of course. I mentioned earlier that the first technology to talk about was something called expression trees. Is anyone here familiar with expression trees? That's pretty good. That's like almost a third or maybe a quarter. So for the rest, expression trees are a feature of the C# language. They came in, I think, around C# 2, I believe, when generics were introduced. And the reason they were introduced was for link, so that you could write some code that looked like regular C#, select this from that, where this, blah, 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 and it would translate it under the hood into SQL. And that was a form of code generation to begin with. But it turns out that these expression trees can just be generally used to generate this code on the fly. Now, the nice thing about expression trees is that the API is really friendly, very easy to use, and it lets you do things that you can't do in C#. Like, for example, if you've got some object and you've got some private members inside of it, I can use expression trees and reflection, .NET reflection, to go and actually create a fast way of accessing those private members. So you could make a library which copies an object just by reading all of the privates and into a new object. The problem with it, which is especially a problem in recent time, is that expression trees aren't fully supported on ahead of time compiled projects like iOS. So if you're doing Xamarin development, then you pretty much can't use these to make fast generated code. And the final downside is that not all parts of the language are supported. So I can't use async, for example, in generating this code. And it becomes fairly limited when you want to do things that are not, sort of simple in a way. If you want to use some fancy language constructs, they're just not there. But let's show you what they look like anyway. Can everyone read this? All right. So here is a very simple program that shows you how to generate a little bit of code using an expression tree. And throughout all of these examples, all we're going to do is generate a function which just takes two numbers and adds them together and returns a result. So in order to do that with expression trees, you can see you import the expression trees, expressions from the link namespace, and this is the crux of it here. You create, using the expression tree API, a new lambda that takes an int and another int and returns an int, and then just has one statement in the body. Add two things together. These two parameters that we then specify later to be parameter A and parameter B. It's really this simple, so I'm not going to go too far into it, but you can just now take that expression and compile it, and then you run it. So under the hood, what happens is the expression compiler will take this and turn it into .NET bytecode, and then that'll get executed by the .NET just-in-time compiler. And I'll kind of talk a little bit about that in a moment. But it's all up on GitHub. There's a repo there. And luckily, this does print our number 3, which is the result of 1 plus 2. So let's blaze right past that. I think this is more interesting. IL generation. So this is using the reflection.emit APIs in .NET to dynamically create types of methods. And there's really one reason why I would say that you want to ever look at these APIs, and that is if you need to be able to generate code which does things you can't express in C#. So that might be things like accessing private members. You might be doing things like, if anyone's seen the unsafe APIs that are new in .NET Core, or ref returns, all sorts of really low-level, hardcore sort of stuff. It turns out that this sort of stuff is very useful when you're writing like a serialization library. So it's good to know this. Now, the downside, super sucks, is that it's extremely verbose because IL essentially it's an assembly language that .NET runs on. It's almost impossible to debug because if you have a problem in IL, in this code that you generate, you'll just get like a very opaque error. You won't be able to breakpoint at a particular line. You won't be able to see what the contents of the stack are. You're pretty much stuffed. And because it's just machine code essentially, you don't get async, you don't get enumerables, you don't get any higher level abstractions, you don't get loops. And yeah, again, it's not supported on AOT platforms.
Why is it in the reflection namespace?
That's a good question. Why is it in the reflection namespace? I actually don't know. And I've never questioned it either. Where would you put it? Give it its own namespace.
Yeah. I wonder if the same team wrote it.
Yeah, probably. I mean, they might have introduced it as part of doing link, and maybe reflection came as.
I think it predates link.
Does it?
Yeah.
Okay. Was it in like 1.0 or something?
Yeah.
Well,
Sorry.
we can ask the team. I don't know. Maybe we'll ask on Twitter. Now, I just thought I'd blind you all. So I talked about this thing called IL. I didn't really explain what it was. So I thought I probably should throw in a slide here that tells you roughly how how C# code ends up getting run on the computer. And it sort of happens in two phases. Your C# compiler reads that code and it translates it into two things. This is essentially, this blue box here is like a DLL, an assembly. It translates it into some metadata which talks about, hey, there are these functions that are exported and this method needs locals to be initialized and blah, blah, blah. and then this IL language, Common Intermediate Language. So it's like a bytecode or an assembly language that the .NET virtual machine understands. Then when you go and execute that, the just-in-time compiler comes and takes that intermediate language code, it turns it into x86 code or ARM code or whatever it needs to be so that it can actually run on the processor underneath, right? So we're coming in and we're writing code right here. And when we use expression trees, we're also essentially emitting this code right here. Now, what does IL actually look like? People just call it IL, by the way, not CIL. If I was to write a method like add that takes A and B and adds them, it would just be 4 instructions. We just load argument 0, load argument 1, and what this does is it takes argument 0 from the stack, from the current method context, pops it onto the stack, and then this add method takes both of those arguments and just pushes, adds them together and pushes the result onto the stack, and return just returns back to the caller. So the result of this is you've got 4 instructions that end up adding 2 numbers together, right? Whatever you passed. So far, so clear? Great. All right, let's show an actual example and hope the demo gods are kind. Okay, so that looks a bit small. So here's an example of, really briefly, can everyone read this? Good. So here's an example really briefly of how to do that same add function, but using IL instead of expression trees. So you basically just want to work with this dynamic method type, which lets you emit one after the other IL codes into it. And so you can generate simple methods, add in these 4 instructions we saw earlier, and then create delegate, essentially just makes this a method using in the CLR underneath, right? And if we were to go and execute this, I hope it's not slow. We see it totally blows up. But the error message is on the wrong screen. And that's unreadable, but it says common language runtime detected an invalid program. Something's wrong with this code, but it doesn't even tell us what or where or any information. It's really hard to get that info, but can anyone see what's wrong with this code here?
The previous one, you're missing LDR underscore 0.
That's right. So I used the wrong variant of some opcode, and instead of loading argument at position 0, I loaded an argument at the position which should have already been on the stack. So if I had, if I put 0 onto the stack, then this would be fine, but I don't have that. So in this case, I would need to actually go and...
So if you did load arg 0, then just load arg, that would work?
No, I would have to do something like this, and this is live coding, so I have no idea. It should be LDC I40. Okay. Okay, and what that says is load constant value, integer, 4 bytes, and it's the number 0. So it's got, .NET has built-in opcodes for the first 16 numbers, right? So hopefully this works. I was just going to change it to load arg 0, but...
This is more fun.
What? This is more fun. It's like F# live coding. And it didn't work.
Just like F# live code.
And I have no idea why.
Just go back to the underscore 0.
Yeah.
Just fix it the way it's supposed to be.
Although, you know what we can do? Actually, no, we can't do that. Let's not worry about it. Let's bail on this. Let's fix it the way we know how. Please work. Okay, it worked. The number 3 is there. We're good. Thanks. Okay, so that is like a fairly simple example, but when it comes time to start writing things a little bit more complex than that, you need to start having a more deliberate way of how you go about it. So here's some code from the Orleans code base. And without worrying too much about what it does, I'm trying to zoom in, but this Surface Book's so slow.
You can read it.
Yeah, okay, good. So I think the best way to, if you are going to do IL code generation, is to see the comments here, C#, I'm like, this is what it would be in C#. So if I'm wrong about this, you know, if something's broken, I can at least try and say, okay, well, is that what this actually translates to, right? And this method ends up being not the most trivial, and it's got, you know, if statements and things in it and whatever, and it's, you know, when things get complicated, it really helps to sort of break it down into pieces like this.
Why do you have to generate it then if you can just sort of write the C# on top of it? Like, I don't know, but
Because
that was going to be my
because
Show
some
the
of
good
these
question.
types, some of these, here's a good question. Some of these types aren't known until I actually go and execute this. So I can't put those types in there.
Placeholder stuff.
Yeah, and actually, in a sense, we use code generation to patch over the lack of expressibility in the language, right? So a language like F#, you'll need code generation less because it can do more for you in that sense. And actually, F# has something called quoted expressions, which I believe allows you to do a lot of this just using F# code that you can then execute, kind of similar to expression trees, but I guess a little bit more intuitive.
So you're going to rewrite all these in F# then?
No. God, no. That would, F# slow, sorry. Okay, so the big question is, how the hell do I know what code to generate? So I want to use IL for generating some code, but I don't know what the opcodes are. And the answer is linkpad, my friend. You open up linkpad, you write the code you want, and then next to the results window that would normally just show, you know, the result of executing this thing, it'll actually also show you what the C# compiler compiles that into. And so you can just go and rip this out and maybe try it with a few different types and see if it changes the arguments at all. And then essentially transplant that. So we've got this method here called shoutout. It's generic for some reason. And it takes some input and then it writes, input is seriously handy, right? And we can see that what that translates into is we load this constant string, blah is seriously handy. We take the first argument, and the reason it's not 0 here, by the way, this method's not static. So implicitly, this is argument 0. We box it because we don't know if this is a struct or an object. And then we just call string.format on these two things, and then write it the result, right? So I guess it's not too tricky to understand when you're only looking at small pieces of IL. Anyway, linkpad is bloody invaluable. Okay, and if you've got ReSharper, you can actually just use the IL viewer that comes in VS as like a ReSharper plugin. Or .peek is a great tool that I use a lot. Again, part of the JetBrains suite. All right, now, so that's IL, good for the low-level stuff, but what I really want to tell you to use is direct syntax generation. So a few years ago, the C# compiler was rewritten, you know, totally managed compiler, Roslyn, right, is the name of the compiler now. And you can actually directly use Roslyn's APIs to go and construct these syntax trees and then compile them. And the benefit is that you can access everything. You've got, you know, async await, value tuples, and, you know, destructor operators and whatever. It fully supports iOS and all the AOT platforms because it's just C# code. You can debug it, which is great. People like that. You can sort of read it. Now, the problems with this, the reason you can't always use it, is that you have to obey the C# rules, right? So I can't go and write crazy code that uses some imaginary construct in my brain that doesn't obey C#'s rules. I can't access privates. I can't write to read-only fields, which is, surprisingly enough, something you can do if you use IL and just the right set of incantations.
So why is this supported on iOS, reflection.emit isn't?
the reason that this is supported on iOS is because you can do this at build time. So I can read, using the Roslyn APIs, I can read the source code of the program I'm writing. You know, your application, I can say, oh, okay, he needs a serializer for this type, or whatever it is. And then I can go and write some C# code to disk just before compilation happens, which is really nice, right? Because then there's no futzing around with reflection, and it works everywhere. And
But if you were doing some sort of plugin library where you didn't know the type beforehand, you'd still run across the same problems.
so if you were going to do something where you needed to generate code at runtime, then you still can't do that on AOT platforms because, you know, Apple's like, no, no one's allowed to do this, right? It's not like a limitation of ARM or anything. It's just Apple's jerks, and Microsoft, because they don't let you do runtime code generation if you're in the Windows Store. So you've got to be fully AOT. Anyway, so yeah, one thing to remember though is that Roslyn's a compiler. It's not built for generating code, right? So the APIs can sometimes be a little funky to work with. And what do these syntax trees look like? Well, if we take our, you know, a simple expression like 1 plus 2, then in Roslyn parlance, it creates this object model with, you know, a class for basically every different type of construct in the language. So an add expression, a numeric literal to represent the 1, and it even includes things like the white space and comments around it. And actually, that's the difference between in Roslyn, we call them concrete syntax trees, not abstract syntax trees, because they are, you know, they're full fidelity between the code that you write in C# and this object model here. So you can translate between them back and forth. They're not abstract in that sense. They're like concrete trees. A full program gets out of hand pretty quick, but you know, you can build them up over time. So here's what it looks like to generate some fairly simple code that doesn't do anything at all using Roslyn. So we generate a namespace we with a class powerful that has nothing in it. And the key to this code here, where we're calling this compilation unit function, is that we're using static of the syntax factory here. So we don't have to type syntax factory.compilation unit. It'll fill that in for us because we've imported it like that. So going from top to bottom, what we're doing here, we create this compilation unit, which was the top node that you saw on the previous slide, if you're looking closely. And then inside that, a namespace we, and inside that, a class powerful. We tell Roslyn to go and insert the normal looking white space, like new lines and tabs, because otherwise it'll just be all on one line and it won't be readable. And then we just turn that syntax tree object model into a string and print it out. Now, the thing is, when you're doing code generation using Roslyn, you've got some choices you need to make. You know, do you want to input, for the input, do you want to take a compiled binary, and then do you want to read it using reflection APIs? Or do you want to use the much more difficult system.reflection.metadata class, which is like a really raw sort of P file parsing library? Or do you want to do source code analysis and then use Roslyn's code analysis APIs? You can also just write a custom parser. And then as for output, either you can compile it at runtime or you can write the source file to disk, right? And in this case, obviously that's not supported on AOT, but in Orleans, we do both. So we say, usually people will write the source to disk and they'll, at build time, will go and generate a C# file. But sometimes if they're using a language like F# and our code generator only understands C#, we'll just compile that in memory the first time they load the app. So we'll just invoke Roslyn, compile it, and load a DLL. And so that allows us to support more languages than we otherwise could. Because unfortunately, we use reflection APIs. And they can be a little bit rough. If it was written today, we'd be using these code analysis APIs, but we'd lose F# support. All right. If you start writing serious code generators, I would recommend taking a general strategy like this. You have your input, whatever shape that is, and you have two phases. Phase one, you generate some kind of metadata model out of it, like you read all the types and you create this, this is what I'm going to generate code from. And then phase two, you take that model and go and generate the actual code. And I'll show you an example of doing that. I've got this serializer. It's kind of like protocol buffers, but it's more sort of .NET friendly, called Hagar. It's just a side project of mine. And it uses Roslyn, and it reads source files, uses code analysis APIs, and then outputs source files. Okay, hopefully readable. All right, you can see this sort of general sort of model here. I've got this type description that's a description of the type you want to create a serializer for. And the type has like a name, and it's got a list of members, properties or fields. And then properties and fields are described above, and they've got a little bit more info. You don't really have to understand it, of course. And then this is what code generation looks like. Again, the first thing we do is we go over the types, and we create this metadata model. And then the next thing we do is we go over the metadata model, and we generate actual C# code as a syntax tree. And then somewhere down here, we sort of string all that together into a compilation unit. We put it all into a namespace. We add all the things that we generated, all these members, and away we go. Okay, so what does this actually end up looking like? Generated code, that is. Okay, let's say that we've got some type, and it's like a transaction, like a bank account transaction. And we're looking at this one here, deposit transaction. It's got a deposit amount and a couple of other fields. What does the code that we generate for this type look like? And I really hope that we can actually see it. It looks like I'm going to have to go and load it from disk. So before I came in here, MSIT, because this is a Microsoft laptop, they decided it'd be cool to install updates. And you can't stop them. They're really unstoppable. You can Control-Alt-Delete it, but they know all the tricks.
It's almost like the event.
So one time I found a way to stop it. I opened it up in the debugger, and I just put it into an infinite loop, so I could go and have lunch and then deal with it later. Keeping all my stuff open.
And then learn how to fix it.
I think after a while they remotely restart your computer. So it's seriously, they're jerks. Actually, they won't let my phone log onto email anymore because it's an Android, it's rooted, and so they're like, no, sorry, you're out. Bloody hell. Okay, this is in test screen interfaces. So if anyone has any questions while I'm doing this, take a moment.
What did Hagar do? Source to source?
So it reads C# source files from a project that you might have, and then it'll generate a serializer for it. So if you're familiar with protocol buffers from Google, it's like a library that Google use internally to transmit objects over the wire and store them in disk. Now it's good because it allows you to change those types, change fields and add members and whatever else, and still have them readable by old versions. And it turns out that's pretty tricky. And in C#, there's nothing really that can do that also supports C#'s more rich object model. We can have a field like object or something, right? Who knows what type you're actually going to throw in there at runtime? You might put in a person, or you might put in a cat. In protocol buffers, you can't really model that very nicely, so people have to resort to layering things above it. And anyway, so this serializer does that more natively. Finish it. Okay. So it's a big file. That means VS Code is going to take a while to add IntelliSense and coloring and stuff. But that Poco you saw before ends up getting translated by the code generator into this kind of big monstrosity of a thing. You can see we're already 42,000 lines in. Right? It does a lot of stuff. But at the end of the day, these things are they all end up being pretty simple, right? A serializer is just saying, take field 1, write that field into the stream. Take field 2, write that field into the stream. And for things like version tolerant serializers like protocol buffers, it's not that much more complicated. The code ends up looking pretty similar. My point is that you can kind of take a complex problem, decompose it. You can write a code generator to automate it, and away you go. You can write some monstrosity of a file that's literally huge. Okay, now the question is, how do you know what syntax nodes to omit? Does anyone have an idea? Yeah?
Linkpad?
Yeah, it's linkpad. Totally right. So linkpad's pretty good. It turns out that next to that IL thing is also this tree thing, and if you highlight some code, it'll actually show you what the Roslyn tree for that looks like. And this is great because that allows you to see, if I write some C# code, how the hell do I translate it into this other thing? Especially because the language keeps changing, you keep thinking oh crap, what do I do here? And thankfully, Visual Studio also comes with a similar kind of thing where you can just click on a node and it'll show you what Roslyn syntax that is underneath. You just have to install the compiler SDK and away you go. All right, so now the final thing is, what kind of code generation should I use? I've described 3 today. I kind of glossed over expression trees. But if I was you, I would say use Roslyn whenever you can, source to source, using code analysis APIs. And if you really need to abuse something, then use IL. Yeah. Okay, thanks. The code's all up on GitHub. And these 2 things form, there's 2 blog posts that kind of describe a lot of what I just said.